Hello there and welcome back to the Science Sleepy Minds. Picture this. You're standing at the very edge of the solar system, so far from the sun that it looks like just another star, a slightly brighter pinprick among millions. The temperature around you has dropped to something your brain cannot meaningfully process, somewhere around minus 230 degrees Celsius, which is the kind of cold that doesn't just kill you, but seems personally offended by your existence. Out here, the familiar planets are memories. Jupiter is a faint dot. Saturn's rings are invisible. Neptune, the last known giant, is so far behind you that light from the sun takes over 4 hours just to reach it. And yet, somewhere ahead of you, drifting through this incomprehensible darkness, there might be something enormous. Something 5 to 10 times the mass of Earth. Something that has been hiding from every telescope, every satellite, and every curious human being for the entirety of recorded history. You probably will not survive this journey, by the way, not because of the cold or the distance, but because the sheer frustration of searching for something this elusive has a way of wearing a person down to their molecular components. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. Go ahead and drop your location and your local time in the comments. I always love knowing whether you're listening at 2 a.m. from a bedroom in Tokyo or winding down after dinner somewhere in Buenos Aires. It makes this whole thing feel like a quiet global campfire. Now dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You take a breath and you stare into that darkness, and the first thing you need to understand is that this is not a new feeling. Humans have been staring at the sky and suspecting that something is hiding just beyond their perception for thousands of years. The ancient Babylonians tracked 5 wandering lights across the heavens: Mercury, Venus, Mars, Jupiter, and Saturn, and they assumed that was the complete set. For centuries, nobody seriously questioned that count. 5 visible planets plus the sun and moon made 7 celestial bodies, a number that felt tidy and even a little holy. The week has 7 days, partly because of this satisfying arrangement. So when you look out at the void tonight and wonder whether something else is lurking, you are participating in one of the oldest human traditions there is: the suspicion that the map is not finished. The modern version of this suspicion has a name. Scientists call it Planet 9, though some researchers prefer the term Planet X, and a few stubborn romantics still whisper Planet Next at conferences when they think nobody important is listening. The idea is beautifully simple in theory and maddeningly impossible in practice. Observations of certain objects in the far outer solar system suggest that their orbits are being gently herded by the gravity of something large. Not a small chunk of ice or a rogue asteroid, but a genuine planet, something with enough mass to push other objects around from hundreds of astronomical units away. 1 astronomical unit is the distance from Earth to the Sun, about 150 million kilometers. So when scientists casually say this hypothetical world might orbit at 500 or even 1,000 astronomical units, they are describing a distance so vast that your brain will attempt to understand it, fail, and then quietly change the subject. Here is the maddening part. Despite decades of indirect evidence, despite computer simulations that practically beg for its existence, despite the combined efforts of some of the most powerful telescopes ever built, nobody has actually seen Planet 9. Not a photograph, not a confirmed blip on an infrared survey, not even a suspicious smudge on a long exposure image that made someone spill their coffee. The solar system's most wanted fugitive remains at large, and the reason is not that scientists are lazy or that their equipment is broken. The reason is that the universe, in its infinite capacity for dark humour, has constructed a nearly perfect set of obstacles that make finding this world one of the hardest observational challenges in the history of astronomy. You are going to learn about every single one of those obstacles tonight. You'll discover why distance alone turns a super-Earth into something dimmer than a candle flame viewed from another continent. You'll understand why the sheer size of the sky transforms the search into a task that would make finding a needle in a haystack feel like a relaxing afternoon hobby. You'll meet the telescopes that have tried and the astronomers who have aged visibly in the attempt. You will encounter alternative theories that suggest maybe, just maybe, the planet does not exist at all, that the gravitational evidence might be a cosmic coincidence, or, in one particularly wild hypothesis, the signature of a tiny primordial black hole about the size of a grapefruit. Scholars still argue whether the clustering of distant orbits is a genuine gravitational fingerprint or simply an artifact of where we have pointed our instruments. That debate alone could fill an entire evening, and honestly it nearly will. But you're not here to panic about the enormity of the problem. You are here to sink into your pillow and let the story carry you. So settle in. Let your breathing slow. Let the darkness outside your window become the darkness of the outer solar system, and let yourself drift alongside the narrative as we trace the path from the very first accidental discovery of a hidden planet, all the way to the cutting-edge searches happening right now, tonight, while you listen to this. The solar system is not done surprising you. It never has been. And the fact that something this massive could still be hiding in plain darkness is either terrifying or deeply, quietly beautiful, depending on how sleepy you are when you think about it. You drift a little further into the dark, and as you do, you find yourself thinking about how anyone ever managed to find a new planet in the first place. Because the thing about planets is that they do not announce themselves. They do not send invitations. They simply exist, wheeling through the blackness, reflecting a little borrowed light, and waiting with infinite patience for some squinting human to notice them. And for most of history, nobody did. The 5 classical planets, Mercury through Saturn, were known since antiquity because they were bright enough to see with the naked eye, and that was considered perfectly sufficient. The universe had 5 wanderers, the stars had their fixed positions, and everyone was happy. Well, almost everyone. On the night of March 13th, 1781, a German-born musician living in Bath, England, changed the planet count forever, and he did it almost entirely by accident. William Herschel was not a professional astronomer. He was an oboist and composer who had developed an obsessive side hobby of building telescopes in his backyard, which is the 18th century equivalent of someone today spending their weekends constructing radio dishes in the garage. Herschel was methodically surveying the sky with a homemade reflecting telescope when he spotted something unusual in the constellation Gemini. It was a faint object that appeared as a small disk rather than a point of light, and it was moving. His first instinct, charmingly cautious, was to call it a comet. He reported it as such to the Royal Society. But as other astronomers tracked the object over the following weeks and calculated its orbit, a startling truth emerged. This was no comet. Its orbit was nearly circular, far beyond Saturn, and it was enormous. Herschel had stumbled upon the 7th planet, the world we now call Uranus, and he had done it without any theoretical prediction, without any gravitational calculation, and without really meaning to. Sometimes the universe just hands you a planet because you were patient enough to look. Now here is where the story gets properly interesting for your purposes, because the discovery of the next planet was the exact opposite of an accident. By the early 19th century, astronomers had been tracking Uranus long enough to notice that something was wrong with its orbit. The planet was not behaving. It would speed up when it should have slowed down, drift slightly off its predicted path, and generally act like a marble rolling across a table that someone kept secretly tilting. Newtonian gravity was supposed to account for all of this, and yet the numbers refused to cooperate. Either Newton's laws were broken, which was an extremely unpopular suggestion, or something unseen was pulling on Uranus from further out. Something massive and dark and completely invisible to every telescope then in existence. Two mathematicians took on the challenge almost simultaneously, and without knowing about each other, which is the kind of coincidence that makes science feel like a soap opera. In France, Urbain Le Verrier sat down with reams of observational data and essentially reverse-engineered the location of the mystery object using nothing but gravitational physics and an extraordinary tolerance for tedious arithmetic. In England, John Couch Adams performed nearly identical calculations. Le Verrier finished first and sent his prediction to the Berlin Observatory, where astronomer Johann Galle pointed a telescope at the suggested coordinates on the night of September 23, 1846, and found Neptune within 1 degree of the predicted position. 1 degree. On his very first night of looking. The discovery took roughly 30 minutes of actual telescope time, which remains one of the most efficient planet hunts in history, and also one of the most smugly satisfying moments in the annals of mathematics. The reason this matters to you tonight is that Neptune's discovery established a template, a gravitational template. The logic went like this. If a known object's orbit misbehaves, you can infer the presence of an unknown object causing the misbehavior, calculate where it should be, and then go find it. This is the exact same logic that underpins the modern hunt for Planet 9, and it is also the exact same logic that makes the hunt so agonizing, because the method works beautifully when the hidden object is relatively close and relatively bright, and it falls apart spectacularly when the hidden object is absurdly far away and absurdly faint. But in 1846 nobody was thinking about those limitations. They were too busy celebrating and arguing about who deserved credit, a dispute so bitter between the French and British scientific establishments that it makes modern academic rivalries look like polite disagreements over tea. There is a quirky footnote to Neptune's discovery that rarely gets mentioned. Galileo Galilei actually observed Neptune in 1612 and again in 1613, more than 200 years before its official discovery. He recorded it in his notebooks as a fixed star near Jupiter. He even noted that it seemed to have moved slightly between observations, which should have been a screaming clue, but he apparently dismissed the movement and moved on. Historians still argue whether Galileo simply lacked the data to recognize what he was seeing, or whether he was so focused on Jupiter's moons that a slow-moving background object simply did not register as interesting. Either way, Neptune hid in plain sight for centuries, which should give you a small, cold shiver when you think about Planet 9 doing the same thing right now. The gravitational breadcrumb method had proven itself gloriously. One invisible planet predicted, one invisible planet found. So naturally, the next question was obvious. Is there anything pulling on Neptune? Is there another world further out lurking in the dark, tugging on orbits and waiting to be calculated into existence? That question would haunt astronomy for the next several decades and would eventually lead a wealthy, obsessive Bostonian to build an entire observatory in the Arizona desert for the sole purpose of answering it. You're about to meet him, and his story is as strange as anything the outer solar system has to offer. The man who built an observatory to find a ghost planet was named Percival Lowell, and he was exactly the kind of person the late 19th century seemed to produce in abundance. Wealthy, brilliant, slightly unhinged, and absolutely certain he was right about everything. Lowell came from one of Boston's most prominent families, the kind of dynasty where your brother becomes president of Harvard and your sister becomes a pioneering poet, and you decide to dedicate your fortune to proving that Mars has canals built by an intelligent civilization. That last part is not a joke. Before Lowell ever turned his attention to the outer solar system, he spent years mapping what he believed were artificial waterways on the Martian surface. publishing books with titles that radiated confidence and detailed illustrations that radiated wishful thinking. The canals, of course, turned out to be optical illusions, a combination of telescope limitations and the human brain's relentless desire to find patterns in noise. But Lowell was not the type to be discouraged by something as trivial as being wrong. By the early 1900s, Lowell had shifted his obsessive focus to a new target. He called it Planet X, and the logic was the same gravitational logic that had led Leverrier to Neptune. Astronomers had noticed small residual discrepancies in the orbits of both Uranus and Neptune, tiny wobbles that could not be fully explained by the known planets. Lowell believed these wobbles pointed to a massive trans-Neptunian planet, something large and distant enough to tug on the ice giants from the outer dark. He spent the last decade of his life performing laborious calculations to predict where Planet X might be, and he funded extensive photographic surveys from his observatory in Flagstaff, Arizona, scanning plate after plate of the night sky for a faint moving dot. He never found it. Lowell died in 1916, frustrated and planetless, and his observatory fell into a legal and financial tangle involving his widow that delayed the search for over a decade. But the search did resume, and this is where the story gets unexpectedly charming. In 1929, the Lowell Observatory hired a young man from Kansas named Clyde Tombaugh. Tombaugh was 23 years old, had no college degree, and had gotten the job essentially by mailing hand-drawn sketches of Jupiter and Saturn to the observatory and impressing the staff with his meticulous eye. His assignment was straightforward in concept and brutal in execution. Systematically photograph sections of the sky, then compare pairs of photographic plates taken days or weeks apart, looking for anything that had moved. The tool he used was called a blink comparator, a device that rapidly flickered between two images of the same star field so that any object that had shifted position would appear to jump back and forth. It was tedious, eye-straining work. Imagine flipping between two nearly identical photographs of a beach, each containing 1,000,000 grains of sand, and trying to spot the single grain that moved. Now imagine doing that for months. On February 18th, 1930, Tombaugh found his moving dot. A faint speck in the constellation Gemini had shifted between plates taken in January, and after careful verification, the Lowell Observatory announced the discovery of the 9th planet. The world erupted with excitement. Newspapers ran front-page headlines. An 11-year-old girl in Oxford, England, named Venetia Burney, suggested the name Pluto over breakfast. Her grandfather passed the suggestion to an astronomer friend, and within months the name was official. There is something wonderfully human about the fact that the solar system's most distant known world was named by a child who thought the Roman god of the underworld was a fitting patron for a place so cold and remote. But here is the twist that matters for tonight's story. Pluto was not Planet X. It was not even close. Lowell had predicted a massive world, something with enough gravitational muscle to perturb the orbits of Uranus and Neptune. Pluto, as subsequent decades of observation revealed, was tiny, pathetically tiny by planetary standards. Its mass turned out to be roughly 1/5 of 1% of Earth's mass, far too small to cause the orbital wobbles that had motivated the search in the first place. The residual discrepancies in Neptune's and Uranus's orbits that Lowell had obsessed over were later shown to be mostly measurement errors, cleared up when Voyager 2 flew past Neptune in 1989 and provided a precise measurement of its mass. In other words, the gravitational evidence for Planet X had been something of a mirage, and Tombaugh had found Pluto not because of Lowell's calculations, but largely because of his own painstaking diligence and a healthy dose of cosmic luck. Scholars still argue whether Tombaugh's discovery should be considered a vindication of the gravitational prediction method or a spectacular coincidence. The philosophical debate is genuinely interesting. Lowell predicted a planet in roughly the right region of the sky, but for entirely wrong reasons, and Tombaugh found a world that happened to be there but didn't match the prediction in any meaningful physical way. It is a bit like predicting that you will find a lion in your garden based on mysterious claw marks on your fence, and then discovering a kitten. Technically, you found a feline, but the claw marks remain unexplained, and your garden still feels dangerous after dark. Pluto's demotion in 2006, when the International Astronomical Union reclassified it as a dwarf planet, was an emotional earthquake for the public and a quiet relief for many astronomers who had spent years trying to reconcile Pluto's tiny size with its planetary title. The reclassification also reopened a door that had been quietly closed since Tombaugh's era. If Pluto was never the massive planet X, then was there still something out there? Had the original question simply been shelved rather than answered? The solar system beyond Neptune was revealing itself to be far more crowded and far stranger than anyone had imagined, and within that strangeness, a new and far more compelling clue was about to surface. You just need to drift a little further out to find it. You float past Pluto now, that little frost-covered world with its heart-shaped nitrogen glacier and its oversized moon cairn, and you keep going. The sun behind you is barely a bright star at this point, and the darkness ahead feels less like empty space and more like a room where someone has deliberately turned off all the lights. But this room is not empty. It is filled with thousands upon thousands of frozen objects, chunks of ice and rock and ancient primordial material left over from the formation of the solar system 4.5 billion years ago. Welcome to the Kuiper Belt, the solar system's attic, where everything that never became a planet got shoved and forgotten about. Except someone has been rummaging through this attic recently, and what they found does not make any sense. The Kuiper Belt was first proposed as a theoretical concept in the mid-20th century, with astronomer Gerard Kuiper suggesting in 1951 that a band of icy bodies might exist beyond Neptune. For decades it remained a hypothesis, because the objects out there are so faint and so small that detecting them required technology that simply did not exist yet. The first confirmed Kuiper Belt object beyond Pluto, a modest chunk of ice called 9092 QB1, was discovered in August of 1992 by astronomers David Jewett and Jane Liu, who had spent 5 years searching with increasingly sensitive cameras before they finally snagged their quarry. Since then, the catalogue has exploded. Over 2,000 Kuiper Belt objects have been identified, and astronomers estimate that millions more are out there, quietly orbiting in the frozen dark, ranging from pebble-sized fragments to dwarf planets like Eris, Makemake and Haumea, each one a little icy world with its own quirks and personality. Now, if you took all of these distant objects and plotted their orbits on a grand diagram, most of them would behave exactly the way you would expect. Their paths around the sun would be oriented in more or less random directions, scattered like pickup sticks dropped on a table. Gravitational interactions with Neptune over billions of years would have nudged them into a variety of inclinations and eccentricities, producing a messy but statistically unremarkable distribution. This is what the outer solar system should look like: random, chaotic, boring if you're being honest. But a small subset of these objects decided to be deeply, confusingly weird. Starting in the early 2000s, astronomers began noticing that certain extremely distant Kuiper Belt objects, the ones with orbits that carry them far beyond the classical belt into the region, known as the scattered disk and beyond, shared a peculiar alignment. Their orbits were not random. Instead, their long elliptical paths were clustered together in physical space, pointing in roughly the same direction, as though some invisible hand had combed them into alignment. The first object that really turned heads was Sedna, discovered in 2003 by Mike Brown, Chad Trujillo, and David Rabinowitz. Sedna's orbit was baffling. Its closest approach to the Sun was 76 astronomical units, which placed it permanently beyond Neptune's gravitational influence, and its farthest point swung out to nearly 1,000 astronomical units. Nothing in the known solar system could explain why Sedna was on this particular path. It was too far from Neptune to have been scattered there by normal gravitational interactions, and too close to the Sun to be an Oort cloud object drifting in from the deep. Sedna was a misfit, an orbital orphan, and it was not alone. Over the following years, more objects with similarly extreme orbits were identified. Bodies like 2012 VP113, nicknamed Biden at the time for reasons that are more political than astronomical, showed the same suspicious clustering. Their arguments of perihelion, which is a technical way of describing the orientation of their closest approach to the Sun, were bunched together in a way that probability alone could not comfortably explain. Imagine rolling a die 20 times and getting the number 415 times in a row. You would not shrug and call it luck. You would start examining the die, and that is exactly what astronomers began to do with the outer solar system. The statistical significance of this clustering became a subject of heated debate. Some researchers ran simulations and concluded that the odds of this arrangement happening by pure chance were less than 1%, perhaps as low as 0.007%, which in scientific terms is the equivalent of the universe tapping you on the shoulder and whispering that something funny is going on. Others were more cautious, pointing out that the sample size was small, only a handful of objects with well-determined orbits, and that small samples can produce misleading patterns. Scholars still argue whether the clustering is robust enough to demand a dynamical explanation, or whether it might dissolve as more objects are discovered and the statistical picture sharpens. This is one of those debates where both sides have legitimate points, and neither side is willing to buy the other a drink. But for a pair of astronomers at the California Institute of Technology, the clustering was not just statistically interesting, it was a signpost, a gravitational fingerprint. Something large and distant was sculpting these orbits, and the most elegant explanation was the one that echoed all the way back to Leverrier and Neptune. A hidden planet. A massive, slow-moving world on an enormous orbit, its gravity gently shepherding these scattered objects into alignment over millions of years, like a cosmic border collie herding a very uncooperative flock of frozen sheep. The math was compelling. The implications were staggering. And the two men who put the case together were about to ignite a scientific firestorm that is still burning tonight. Right now, while you listen to this with your eyes half closed and the darkness outside your window feeling just a little bit deeper than it did a few minutes ago, the two men at the centre of this storm could not have arrived at the same conclusion from more different starting points. Konstantin Batagin was a theoretical astrophysicist in his early 30s, the kind of person who thinks in equations the way most people think in words. A Russian-born researcher with a side career as the lead singer of a rock band, which is exactly the sort of biographical detail that makes you wonder whether the universe is writing fiction. Mike Brown was an observational astronomer who had already earned the nickname the man who killed Pluto for his role in discovering Eris, the Kuiper Belt object whose size rivaled Pluto's and whose existence ultimately triggered the 2006 reclassification vote. Brown had spent years cataloguing the outer solar system's weirdest residents, and Batagin had spent years building mathematical models of how planetary systems evolve. When they started working together at Caltech, the combination was something like pairing a detective who knows every alley in the city with a forensic analyst who can reconstruct a crime scene from a single footprint. Their collaboration began not with a eureka moment, but with a disagreement. Brown had noticed the orbital clustering of distant Kuiper Belt objects and suspected a planet was responsible. Batagin was skeptical. He figured he could disprove the idea by running simulations showing that the clustering could arise naturally, without any hidden planet. So he set up his computer models, plugged in the known dynamics of the outer solar system, and waited for the simulations to demolish the planet hypothesis. They did not. Instead, the simulations kept producing the same frustrating result. Without a massive perturber on a distant inclined elliptical orbit, the clustering could not be maintained over the age of the solar system. The orbits would randomize within a few 100 million years. Something had to be holding them in place, and the simplest something was a planet. On January 20th, 2016, Batagin and Brown published their findings in the Astronomical Journal, and the paper landed in the scientific community like a boulder dropped into a quiet pond. The title was measured and academic, but the content was explosive. They proposed that a planet with a mass between 5 and 10 times that of Earth was orbiting the Sun at an average distance of roughly 400 to 800 astronomical units, on an orbit so elongated that one trip around the Sun might take between 10,000 and 20,000 years. The planet's gravity, they argued, could explain not only the orbital clustering of the distant Kuiper Belt objects, but also several other previously puzzling features of the outer solar system, including the existence of objects on highly inclined or even perpendicular orbits, and the mysterious detachment of Sedna-like bodies from Neptune's influence. The paper was careful, rigorous, and deeply persuasive to many in the astronomical community. It did not claim to have found a planet. It claimed to have found compelling indirect evidence that a planet should exist, which is an important distinction and one that gets lost approximately every time a journalist writes a headline. The media coverage was immediate and enormous. New planet found in solar system, shouted outlets that apparently did not read past the abstract. Brown and Batagin spent weeks doing interviews, gently correcting the narrative and explaining that predicting a planet and actually seeing a planet are two very different things. Leverrier predicted Neptune and Gall found it within hours, but Leverrier's target was about 30 astronomical units from the Sun. Batagin and Brown's target was potentially 20 times farther away, and as you're beginning to understand, distance in the outer solar system is not just a number. It is a wall. There is a quirky detail about the Batagin-Brown paper that rarely makes it into popular accounts. One of the strongest pieces of supporting evidence was not the clustering itself, but a secondary prediction. Their model predicted the existence of Kuiper Belt objects on orbits perpendicular to the plane of the solar system, objects that had been kicked into extreme inclinations by Planet Nine's gravity. At the time the paper was written, a few such objects were already known, and they fit the prediction neatly. This was the kind of independent confirmation that makes physicists sit up straighter in their chairs. It is one thing to build a model that explains the data you already have. It is considerably more impressive to build a model that explains data you are not even trying to explain, almost like solving a crossword puzzle, and accidentally discovering that your answers also work for a completely different puzzle, printed on the back of the page. Scholars still argue about how much weight to give this secondary evidence. Skeptics point out that the sample of high inclination objects is very small, and that their orbital properties are not perfectly constrained. Supporters counter that the mere existence of these perpendicular orbits is extremely difficult to explain without some kind of massive perturber, and that Planet 9 provides the most parsimonious explanation. The debate is ongoing, and it is conducted with the kind of polite ferocity that academics specialize in, where every sentence is carefully worded and every footnote is a concealed weapon. What Batagin and Brown had accomplished was remarkable. They had resurrected the gravitational prediction method that had worked so spectacularly for Neptune and applied it to the farthest frontier of the solar system. They had given the astronomical community a target, a reason to search, and a testable hypothesis. The world leaned forward. Telescopes turned outward. Search programs were funded and designed. And then, slowly, painfully, it became clear just how impossibly difficult the actual finding would be. Because Planet 9, if it exists, is not hiding behind a curtain you can simply pull aside. It is hiding behind the fundamental laws of physics, and those laws, as you're about to discover, are spectacularly uncooperative when you're trying to photograph something that far away and that faint. You need to understand just how far away 500 astronomical units actually is, because your brain is going to try to process that number, and it is going to fail, and that failure is itself the first clue about why Planet 9 is so impossibly hard to find. So let us build this distance piece by piece, gently, the way you might stack pillows before collapsing into them. 1 astronomical unit is the distance from the Earth to the Sun, roughly 150 million kilometers. That is already a distance that defies casual understanding. If you could drive a car at highway speed without stopping, it would take you about 170 years to cover 1 astronomical unit. Light, the fastest thing in the universe, crosses that distance in about 8 minutes and 20 seconds. So when you look at the Sun, you're seeing it as it was 8 minutes ago, which means in a very real sense you have never seen the Sun in the present tense. You have only ever seen its recent past. This is a mildly unsettling thought that you are welcome to ignore for the sake of your sleep tonight. Now multiply that distance by 500. Planet 9, if it sits at 500 astronomical units, would be 75 billion kilometers from the Sun. Light would take nearly 3 days to travel from the Sun to Planet 9's orbit. The Voyager 1 spacecraft, the farthest human-made object from Earth, launched in 1977, has been travelling for nearly 5 decades, and it has covered roughly 160 astronomical units. It is not even a third of the way to where Planet 9 might be. If you sent a spacecraft toward Planet 9 today using current propulsion technology, it would arrive somewhere around the year 2100 at the earliest. And that estimate is optimistic enough to qualify as science fiction. The New Horizons probe, which flew past Pluto in 2015 and is currently sailing through the Kuiper Belt at about 50,000 kilometers per hour, would need centuries to reach 500 astronomical units. Centuries. You would need to pack not a lunch, but a civilization. Let us try another analogy, because analogies are the only parachutes your brain has when falling through these distances. Imagine the solar system as a football pitch, with the Sun sitting on one goal line. On this scale, Earth would be about 1 centimetre from the Sun. Jupiter would be roughly 5 centimetres out. Neptune, the last known giant planet, would sit about 30 centimetres from the goal line, still comfortably within the 6-yard box. Pluto would be around 40 centimetres. And Planet 9, at 500 astronomical units, would be sitting approximately 5 metres from the goal line, somewhere near the penalty spot, alone in the dark, on a pitch where the floodlights only illuminate the first half metre. Everything beyond that is shadow. You're searching for a single grain of sand sitting on the penalty spot of a pitch where you can only see the goal line, and you have to find it from the stands. This distance does something cruel to light. The Sun, which bathes Earth in generous warmth and illumination, is a fading memory at 500 astronomical units. The intensity of sunlight follows the inverse square law, which means that when you double your distance from the Sun, the light you receive drops to 1/4. At 500 astronomical units, the sunlight is 1/250,000th as intense as it is at Earth. Noon on Planet 9 would look dimmer than the darkest moonless night you have ever experienced. If you stood on the surface of this hypothetical world and looked back toward the sun, you would see a star. A bright star, certainly. Brighter than Venus appears in our sky, but recognizably a star. Not a disk, not a source of warmth. Just a point of light with a slightly personal grudge against you for being so far away. And here is the part that matters most for the search. Planets in our solar system do not generate their own visible light. They shine by reflecting sunlight. The amount of light a planet reflects depends on two things: how much sunlight reaches it, and how much of that sunlight bounces back toward Earth. At 500 astronomical units, the sunlight reaching Planet 9 is already catastrophically faint. But the reflected light has to travel all the way back, another 500 astronomical units, to reach our telescopes. This means the brightness drops not just with the square of the distance, but effectively with the fourth power of the distance for reflected light. A planet that would be easily visible at 30 astronomical units, like Neptune, becomes roughly 400,000 times fainter at 500 astronomical units. 400,000 times. That is the difference between a campfire and a single firefly seen from the next county over. There is a mainstream historical fact buried in this math that is worth savouring. When Gal found Neptune in 1846, the planet was roughly 30 astronomical units from the Sun, and it was bright enough to be seen through a modest telescope in a single evening of observing. Neptune's apparent magnitude was about 8, faintly visible with good binoculars. Planet 9, by contrast, is estimated to have an apparent magnitude somewhere between 20 and 27, depending on its size, albedo, and exact distance. Magnitude 25 is approximately the limit of what the Hubble Space Telescope can detect in a deep exposure. So you are looking for something that sits right at or beyond the detection threshold of one of the most powerful telescopes ever launched into orbit. Scholars still argue over the precise brightness estimate, because it depends on assumptions about Planet 9's atmosphere, composition, and surface reflectivity, none of which are known. Some models suggest a thick hydrogen-helium envelope that might reflect a bit more light. Others suggest a darker, icier surface that would swallow photons like a black hole swallows optimism. The distance alone, before you even consider any other obstacle, makes Planet 9 a ghost. A gravitational ghost that tugs on distant icy bodies but refuses to reflect enough light for anyone to photograph it. You're lying in the dark right now, and somewhere out there so is Planet 9, and the darkness is winning. So you now have a sense of the distance, that yawning 500 AU chasm between the Sun and the hypothetical world you're chasing. But distance alone does not kill a search. Distance is just the opening act. The real assassin is brightness, or rather the catastrophic lack of it. And to understand why Planet 9 is so dim that it might as well be invisible, you need to spend a quiet moment with a physical law that governs everything from light bulbs to stars to the faint glow of a frozen planet drifting through the outer dark. The inverse square law is one of those fundamental rules of physics that sounds simple and then proceeds to ruin your evening. It states that the intensity of light from a source decreases in proportion to the square of the distance from that source. Double the distance and the brightness drops to 1/4. Triple the distance and it drops to 1/9. At 10 times the distance you receive 1/100th of the original brightness. This law applies to everything that radiates or reflects light, and it is the single biggest reason why telescopes have limits and why astronomers drink so much coffee. You encountered this law briefly in our discussion of how dim the Sun appears at 500 astronomical units, but now you need to understand how it compounds when you're trying to detect reflected light from a planet rather than direct light from a star. When sunlight leaves the sun and travels outward, it weakens according to the inverse square law as it crosses the solar system. By the time it reaches a hypothetical planet 9 at 500 astronomical units, it has already been reduced to a whisper. But then something has to happen to that whisper for you to detect it from Earth. The sunlight has to hit planet 9's surface or atmosphere, bounce off, and travel all the way back to the inner solar system where your telescope is waiting. That return trip is another 500 astronomical units, give or take, depending on the relative positions of Earth and planet 9. So the light you're trying to detect has made a round trip of roughly 1,000 astronomical units, and it has been weakened by the inverse square law twice, once on the way out and once on the way back. The net effect is that the apparent brightness of a body seen in reflected sunlight drops with the fourth power of its distance from the sun, not the second. This is not a gentle decline. This is a cliff. Let us put numbers on the cliff. Neptune, at 30 astronomical units, reflects enough sunlight to shine at an apparent magnitude of about 7.8, which means you can spot it with decent binoculars on a clear night. If you took an identical copy of Neptune and placed it at 500 astronomical units, its apparent magnitude would drop to something like 26 or 27. That is roughly 1 billion times fainter than what the naked eye can see. 1 billion. You would need one of the largest telescopes on Earth, collecting light for extended periods, pointed at exactly the right patch of sky, under perfect atmospheric conditions, just to have a chance of registering it as a faint smudge barely distinguishable from the noise in your detector. And Planet 9 is probably not an identical copy of Neptune. Current estimates suggest it is smaller, somewhere between 5 and 10 Earth masses, which likely makes it a mini Neptune or a super-Earth. A smaller planet means a smaller cross-section catching sunlight, which means even less reflected light reaching your instruments. There is a quirky historical detail that illustrates this problem beautifully. When Clyde Tombaugh found Pluto in 1930, remember that blink comparator he used? Pluto was shining at roughly magnitude 15. That was faint enough to require long, photographic exposures and painstaking comparison of plates, and it pushed the technology of the era to its limits. Tombaugh spent nearly a year at the eyepiece before he found his moving dot. Planet 9, at its estimated distance, could be 10,000 to 1 million times fainter than Pluto appeared during that search. If Tombaugh were alive today, and you handed him the same task with the same blink comparator, he would look at the numbers, put the comparator back in its box and politely ask if you were joking. Modern detectors are, of course, vastly more sensitive than photographic plates. Charge-coupled devices, or CCDs, can detect individual photons and build up images over time with extraordinary precision. But even the best CCDs have noise, random electronic signals that masquerade as faint astronomical sources. When the object you are searching for produces a signal comparable to, or smaller than the noise in your detector, you have entered a realm where detection becomes a statistical exercise rather than a straightforward observation. You are not looking for a planet. You are looking for a slight excess of photons above the background hiss, and convincing yourself and the rest of the scientific community that those excess photons are real and not a figment of your electronics requires levels of confidence that border on the philosophical. Scholars still argue about the exact brightness Planet 9 would have, because the calculation depends on variables that are themselves uncertain. The planet's albedo, the fraction of incoming light it reflects, is unknown. An icy surface might reflect 20 or 30% of incoming sunlight. A darker, rockier surface might reflect less than 10%. The planet's size is estimated but not measured. Its distance is a range, not a point. Each of these uncertainties shifts the expected brightness by factors that matter enormously when you're already at the bleeding edge of detectability. Some optimistic models put Planet 9 just within reach of current technology. Pessimistic models put it beyond the capability of anything currently operational, and you are left lying here in the dark, contemplating the fact that the universe built a planet and then wrapped it in just enough shadow to make finding it feel like a personal insult directed at the entire field of astronomy. The faintness of Planet 9 is a brutal obstacle, but at least it is an obstacle you can theoretically overcome by building a bigger telescope or a more sensitive detector. The next problem is not so forgiving, because it has nothing to do with your equipment and everything to do with the sky itself. The sky is enormous. Absurdly, oppressively, almost comically enormous. And Planet 9 could be anywhere in a terrifyingly large fraction of it. Think about it this way. You know roughly what Planet 9's orbit might look like. Batagin and Brown's models suggest an elongated ellipse with a semi-major axis of several hundred astronomical units, inclined to the plane of the solar system by perhaps 15 to 25 degrees. But knowing the shape of the orbit does not tell you where on that orbit the planet currently sits. The orbit is so large that it would take Planet 9 between 10,000 and 20,000 years to complete a single lap around the Sun. That means in any given century the planet moves through less than 1% of its total orbital path. It could be near perihelion, its closest approach to the Sun at perhaps 200 astronomical units, where it would be relatively brighter and relatively closer. Or it could be near aphelion, its farthest point at perhaps 1,000 astronomical units, where it would be so faint that even the next generation of telescopes would struggle to detect it. The difference between these two scenarios is the difference between a difficult search and an impossible one, and nobody knows which scenario is real. The region of sky that Planet 9 could plausibly occupy, given the uncertainties in its orbital parameters, spans hundreds of square degrees. To put that in perspective, the full moon covers about half a degree of sky. A professional telescope with a wide-field camera might image a patch of sky 1 or 2 degrees across in a single exposure. Covering the entire search area would require thousands of individual pointings, each one needing long exposures to reach the necessary depth, each one generating gigabytes of data that must be processed, analysed, and compared to previous observations to detect any faint moving object. This is not a weekend project. This is a campaign that spans years and consumes telescope time that could otherwise be used for dozens of other scientific programs, which means every hour spent searching for Planet 9 is an hour not spent studying galaxies or exoplanets or supernovae, and telescope allocation committees are acutely aware of this trade-off. There is a mainstream historical parallel here that is worth pausing on. When astronomers searched for Pluto in the 1920s and 1930s, they had a similar sky coverage problem, but the search area was smaller and the limiting magnitude was brighter. Tombaugh systematically photographed the sky along the ecliptic, the plane of the solar system, in strips, eventually covering a huge swath of the zodiac over the course of about a year. His search area was large but manageable because Pluto was expected to be relatively close to the ecliptic plane. Planet 9, with its predicted orbital inclination, could wander significantly above or below the ecliptic, vastly expanding the search volume. Tombaugh was scanning a hallway. Planet 9 hunters are scanning a ballroom in the dark with a flashlight that illuminates one floor tile at a time. Modern survey telescopes have made the flashlight considerably brighter, but the ballroom has grown proportionally. The Panoramic Survey Telescope and Rapid Response System, known as PAN-STARRS, operating from Hawaii, has surveyed most of the visible sky multiple times, reaching impressive depths. The Dark Energy Survey, originally designed to study the accelerating expansion of the universe, has covered a large patch of the southern sky with extraordinary sensitivity. The Zwicky Transient Facility, perched on Mount Palomar in California, scans the northern sky repeatedly, looking for anything that changes or moves. Each of these surveys has been examined and re-examined for signs of Planet 9, and each time the result has been the same, nothing confirmed. Not because these telescopes are inadequate, but because each survey has its own combination of sky coverage, depth, and cadence that leaves frustrating gaps in the search. Here is a quirky detail that captures the absurdity of the situation. Astronomers have estimated that the existing surveys, taken together, have only ruled out Planet 9 in a fraction of the possible parameter space. Depending on whose analysis you trust, somewhere between 30 and 70% of the plausible search region has been covered to the necessary depth. That means there is a substantial chunk of sky where Planet 9 could be sitting right now, happily orbiting, gravitationally shepherding distant ice balls, and completely undetected because no telescope has stared at that particular patch long enough or deeply enough to catch it. Imagine losing your keys in a house with 100 rooms and having searched 60 of them. The keys might be in room 61, or they might be in room 99, and every room takes a week to search properly. Scholars still argue about exactly how much of the search space has been effectively covered, because the answer depends on assumptions about Planet 9's brightness, which, as you already know, depends on assumptions about its size, distance, and albedo. A slightly smaller, slightly darker planet could be hiding in regions that have technically been surveyed, but not surveyed deeply enough to detect something that faint. The search is not just about pointing the telescope in the right direction. It is about pointing the telescope in the right direction with enough sensitivity to catch a ghost, and the ghost keeps adjusting its camouflage every time you update your models. You pull your blanket a little tighter and realize that the sky above your roof is not just big. It is adversarial. It is a puzzle built by physics with no obligation to be solvable within a human lifetime. And Planet 9 knows this better than anyone. You might be thinking, as you lie there with the ceiling slowly blurring into a comfortable nothing, that there has to be a smarter way to do this. If reflected sunlight is too faint to catch, why not look for something else entirely? Why not look for the planet's own warmth? This is an excellent thought, the kind of thought that has kept infrared astronomers employed for decades. And it is also the kind of thought that leads directly into another beautifully constructed dead end. Every object in the universe with a temperature above absolute zero emits thermal radiation. You're doing it right now. Your body is radiating infrared light, which is why thermal cameras can see you in complete darkness, glowing like a soft, warm ghost against the cooler background of your bedroom walls. Planets do this too. Even a frozen world at 500 astronomical units is not at absolute zero. It has some internal heat, left over from its formation billions of years ago, slowly leaking outward through its atmosphere or surface. For a planet with 5 to 10 Earth masses, models suggest an effective temperature somewhere in the range of 30 to 50 Kelvin, which translates to roughly minus 220 to minus 240 degrees Celsius. That is profoundly cold by human standards, but it is still warm enough to emit faint infrared radiation, and infrared radiation does not depend on reflected sunlight. It comes from the planet itself, so in principle you could detect Planet 9 by its own glow, even in the absence of any reflected light, which sounds like a wonderful loophole in the universe's otherwise airtight security system. The telescope that was supposed to exploit this loophole was called WISE, the Wide Field Infrared Survey Explorer, and it launched in December 2009 on a mission to survey the entire sky in infrared wavelengths. WISE was a remarkable instrument. It carried a telescope cooled to near absolute zero by a block of solid hydrogen, which prevented the telescope's own heat from drowning out the faint infrared signals it was trying to detect. Over the course of about 10 months, WISE scanned the entire sky twice, cataloguing hundreds of millions of infrared sources from distant galaxies to nearby brown dwarfs. It was by any measure an extraordinary success, and when the data was searched for signs of a large undiscovered planet in the outer solar system, the result was silence. WISE did not find Planet 9, neither did its successor mission, NEOWISE, which reactivated the spacecraft in 2013 using its 2 shorter wavelength infrared channels after the solid hydrogen coolant had been exhausted. The reason is a familiar one by now: sensitivity. WISE was designed to detect objects that were relatively warm by astronomical standards, things like brown dwarfs with temperatures of several hundred Kelvin or asteroids warmed by proximity to the Sun. A planet at 40 Kelvin, emitting most of its thermal radiation at wavelengths longer than what WISE's detectors were optimized for, fell below the sensitivity threshold. The telescope could see warm things beautifully. It could not see very cold things at very great distances, which is exactly what Planet 9 is. It is as if you built a metal detector sensitive enough to find a coin buried 6 inches underground, and then someone asked you to find a coin buried 60 feet underground. The physics is the same. The scale defeats you. There is a mainstream astronomical fact woven into this frustration that deserves attention. WISE and NEOWISE did successfully rule out the existence of any Saturn mass or larger object within about 10,000 astronomical units and any Jupiter mass object within about 26,000 astronomical units. This is genuinely useful information. It means that whatever is out there, if anything is out there, is not a gas giant of the familiar type. It has to be smaller, colder, and fainter than the upper limits these surveys established. This narrows the parameter space and pushes Planet 9 into the super-Earth or mini-Neptune category, which is consistent with Batagin and Brown's models, but also makes the detection problem even harder, because a smaller planet has less surface area to radiate heat, and therefore an even fainter infrared signature. Scholars still argue about whether future infrared missions could succeed where WISE fell short. The James Webb Space Telescope, with its extraordinary sensitivity in the mid-infrared, has been suggested as a potential Planet 9 hunter. But JWST has a critical limitation for this purpose. Its field of view is tiny. It is designed to stare intensely at small patches of sky with breathtaking precision, not to survey enormous swaths of the celestial sphere. Using JWST to search for Planet 9 would be like using a jeweler's loupe to search a football pitch. You would see every blade of grass in exquisite detail, but you would cover approximately none of the ground. The telescope you need is one that combines wide field coverage with deep infrared sensitivity, and as of right now, while you lie here breathing slowly and letting the warmth of your bed contrast with the cold of the story, no such telescope exists in a fully operational state. There is a quirky footnote to the WISE saga that brings a wry smile. When Kevin Luhman at Penn State conducted a thorough analysis of WISE data in 2014, specifically searching for distant planets and nearby brown dwarfs, he titled his paper with a kind of understated academic humour that only astronomers truly appreciate. The conclusion was essentially, we looked everywhere and nothing is there, at least nothing above our detection limits. The absence of evidence, as the saying goes, is not evidence of absence, but it is certainly evidence of frustration. The infrared window, once the great hope for sidestepping the reflected light problem, had offered a view of the outer solar system and shown it to be, at least at the wavelengths and sensitivities available, maddeningly empty. So reflected sunlight is a whisper, and thermal radiation is a murmur, and you are beginning to appreciate that Planet 9 has dressed itself in a cloak woven from the fundamental physics of light and distance. But surely you think modern survey telescopes are powerful enough to overcome these problems through sheer brute force? Surely if you photograph the sky enough times, deeply enough, with enough computing power crunching the data, something will turn up. This is a reasonable hope, and it is the hope that has driven some of the most ambitious astronomical surveys in history. It is also a hope that has been systematically disappointed, not because the surveys failed, but because each one was built with its own set of trade-offs that left just enough room for Planet 9 to slip through. Let us take a tour of the telescopes that have tried, because their stories tell you as much about the difficulty of the search as any equation. Start with Pan-STARRS, the Panoramic Survey Telescope and Rapid Response System, perched atop Haleakala on the island of Maui. Pan-STARRS was built primarily to detect near-Earth objects, asteroids and comets that might one day threaten our planet, and it does this by photographing large sections of the sky repeatedly and looking for things that move. It has surveyed most of the sky visible from Hawaii to impressive depths, reaching objects as faint as magnitude 23 or 24 in its best exposures. That sounds deep, and it is deep, but recall that Planet 9 might be magnitude 25 or fainter. Pan-STARRS gets close to the target but does not quite reach it, like a ladder that gets you to the second floor window but not the third. The data has been searched extensively for Planet 9 candidates, and while it has revealed thousands of new Kuiper Belt objects and other solar system bodies, the big prize has not appeared. Next, consider the Dark Energy Survey, which used a powerful camera mounted on the 4-meter Blanco telescope in Chile. The DES was designed to map hundreds of millions of galaxies across a large swath of the southern sky, studying the distribution of matter in the universe to understand dark energy. As a side benefit, its deep, wide-field images were excellent hunting grounds for distant solar system objects. Researchers combed through DES data and discovered several new extreme trans-Neptunian objects, some of which added to the evidence for orbital clustering. But Planet 9 itself remained absent from the images. The DES covered only a portion of the sky, roughly 1/8 of the celestial sphere, and while it went deep, it did not go deep everywhere. Some regions were observed more thoroughly than others, and the cadence of observations, how often the same patch of sky was revisited, was optimized for galaxy surveys rather than for detecting slow-moving solar system objects. The survey was a fishing net designed for a different kind of fish. The Zwicky Transient Facility at Palomar Observatory in California takes yet another approach. ZTF scans the entire visible northern sky every few nights, looking for transient events like supernovae, variable stars and moving asteroids. Its strength is cadence, the sheer frequency with which it revisits the same fields, which makes it superb at catching things that change or move on timescales of days to weeks. But its depth is limited compared to DES or the upcoming Vera Rubin Observatory. ZTF reaches about magnitude 20 to 21 in a typical exposure, which is nowhere near deep enough to detect Planet 9 at most of its predicted distances. It would catch Planet 9 only if the planet happened to be near its closest approach to the Sun, at perhaps 200 astronomical units, where it would be at its brightest, and even then only if it wandered through the northern sky. ZTF is a speed reader scanning every page of a library, but it cannot read the fine print. Here is a historical fact that puts these modern efforts in perspective. When the asteroid Ceres was discovered in 1801 by Giuseppe Piazzi, it was found with a telescope that had an aperture of about 7.5 centimeters. The entire discovery was made with an instrument you could hold in your hands. 2 centuries later, astronomers are using telescopes with mirrors 4 to 8 meters across, backed by digital detectors that are millions of times more sensitive than the human eye, and they still cannot find Planet 9. The target has retreated so far and become so faint that the exponential improvement in technology has been almost perfectly matched by the exponential difficulty of the problem. It is an arms race between human ingenuity and cosmic indifference has home field advantage. Scholars still argue about whether the combined data from existing surveys should have found Planet 9 already if it exists in the most favourable part of its predicted parameter space. Some analyses suggest that if Planet 9 is near perihelion and has a reasonably reflective surface, it should have appeared in at least one of these surveys by now, and its absence might indicate that it is farther away, darker, or smaller than the optimistic models suggest. Other analyses argue that the gaps between surveys, the regions of sky not covered to sufficient depth, are large enough to comfortably hide the planet even in favourable scenarios. There is a quirky detail that drives this uncertainty home. Different research groups analysing the same survey data have reached different conclusions about how much of the search space has been effectively ruled out. Because they use different assumptions about the planet's properties, the search is not just limited by telescopes, it is limited by the fact that you do not entirely know what you're looking for, and every assumption you make about the target changes the map of where you should have already found it. There's another obstacle hiding inside the search, one that is subtler than faintness and more insidious than the vastness of the sky. It has to do with how Planet 9 moves, or more precisely, how it appears to move from our vantage point, and the answer is barely at all. This near-total stillness against the background stars is one of the most underappreciated reasons why the planet remains unfound, and it strikes at the very heart of how humans have always discovered new objects in the solar system. Every planet ever identified, from Herschel's accidental sighting of Uranus to Tombaugh's patient blinking at Pluto, was found because it moved. Motion is the tell. Stars are so far away that they appear fixed on human timescales, pinned to the celestial sphere like sequins on a dark curtain. Planets, asteroids, and comets, being much closer, drift against this fixed background over the course of hours, days, or weeks, and that drift is what distinguishes them from the stellar wallpaper. Tombaugh's blink comparator worked precisely because Pluto shifted noticeably between photographic plates taken days apart. The method is ancient and reliable. Take two pictures of the same piece of sky, compare them, and look for the dot that jumped. If something moved, it is in the solar system. If it did not, it is a star, and you move on. Planet 9 demolishes this method through sheer sloth. At 500 astronomical units, the planet's orbital velocity is glacially slow, perhaps 2 to 3 kilometers per second compared to Earth's 30 kilometers per second. But orbital velocity is only part of the story. What matters for detection is not how fast the planet actually moves through space, but how fast it appears to move against the background stars as seen from Earth, and this apparent motion, called proper motion, shrinks dramatically with distance. An object at 500 astronomical units, even one moving at a reasonable orbital velocity, would appear to crawl across the sky at a rate of roughly 1 to 2 arcseconds per year. An arcsecond is 1/3600th of a degree. To visualise this, hold a coin at arm's length. That coin covers about 1 degree of sky. Now imagine dividing the width of that coin into 3,600 equal slices. Planet 9 moves 1 or 2 of those slices per year. This means that if you take 2 images of the same star field a week apart, which is a typical cadence for many surveys, Planet 9 will have moved so little that it is essentially indistinguishable from a stationary object. You need images separated by months or even years to detect any meaningful shift, and over those longer timescales, a host of other problems creep in. The atmospheric conditions change, the detector characteristics drift, the background stars subtly shift due to their own tiny proper motions. Comparing images taken many months apart is exponentially harder than comparing images taken days apart, because you have to account for all of these changes before you can confidently identify a faint moving source. It is like playing one of those spot the difference puzzles, except both pictures have been slightly rotated, slightly faded, and someone has added a few hundred extra details to distract you. There is a mainstream historical fact here that sharpens the contrast. When Neptune was discovered in 1846, it was moving at a rate of about 22 arcseconds per year, which is roughly 10 to 20 times faster than Planet 9's predicted motion. Neptune was practically sprinting by comparison, and it was bright enough to be obvious in a single night's observation once Galler knew where to look. Planet 9 offers neither the speed nor the brightness. It demands that you detect a faint smudge, and then wait months to confirm that the smudge has drifted by an amount smaller than the width of a human hair seen from across a room. Here is a quirky complication that makes this even worse. At such slow apparent speeds, Planet 9 can be confused with other things that appear nearly stationary. Distant galaxies, faint background stars, and imaging artifacts all produce point-like or slightly extended sources in astronomical images. Most survey pipelines are designed to flag fast-moving objects, asteroids and near-Earth objects that shift noticeably between exposures taken the same night, and to catalogue stationary objects as stars or galaxies. Planet 9 falls into a detection gap. It moves too slowly to trigger the moving object pipelines, and too faintly to stand out in the static object catalogues. It occupies a twilight zone between the categories that astronomers have built their software to handle, which means finding it may require custom algorithms specifically tuned to detect extremely slow-moving, extremely faint sources in multi-epoch survey data. Scholars still argue about the best computational strategies for this kind of search. One approach is called digital tracking, or shift and stack, where you take multiple short exposures of the same field, shift each image by a small amount corresponding to a hypothesized motion vector, and then stack them together. If an object is moving along that vector, its light accumulates coherently, and it emerges from the noise like a signal rising out of static. The problem is that you do not know the motion vector in advance, so you have to try thousands or millions of possible vectors, each one corresponding to a different possible orbit, and search the stacked image for each one. The computational cost is staggering. You're essentially asking a computer to play millions of rounds of a guessing game, and for each guess, it must process gigabytes of imaging data. Some research groups have developed clever shortcuts using graphics processing units and machine learning to speed up the process, but even with these tools, the search remains formidable. Planet 9's apparent stillness is not just an inconvenience. It is a fundamental barrier that turns a photographic search into a computational marathon, and the finish line keeps receding. As if the faintness and the stillness were not enough, Planet 9 has another trick up its sleeve, and this one involves the Milky Way itself conspiring to hide it. You've probably seen the Milky Way on a clear dark night, that luminous band of soft light arching across the sky, and you may have found it beautiful. It is beautiful. It is also, from the perspective of someone trying to find a faint, slow-moving object in the outer solar system, an absolute nightmare. The Milky Way's band of light is produced by billions of stars in the disk of our galaxy, too numerous and too densely packed to be resolved individually by the naked eye, so they blur together into that familiar milky glow. When you point a telescope at the galactic plane, the region where this band is thickest, the image explodes with sources. Stars of every magnitude crowd the field, overlapping, blending, creating a dense, luminous fog through which faint objects become extraordinarily difficult to detect. Astronomers call this stellar confusion, and it is one of the oldest problems in observational astronomy. Trying to find a faint moving object in a dense star field is like trying to hear someone whispering your name at a rock concert. The signal is there, theoretically, but the noise is overwhelming. Planet 9's predicted orbit does not stay conveniently away from the galactic plane. Depending on the orbital models you use, a significant fraction of the planet's possible path crosses through or near the Milky Way's densest star fields. Some models place Planet 9's current position in or near the constellations of Orion, Taurus or Gemini, regions that lie relatively close to the galactic plane and are packed with background stars. If the planet happens to be in one of these regions right now, which is entirely possible given the uncertainties, it could be buried behind a curtain of stellar light so thick that even a dedicated search with a powerful telescope might not be able to pull it out. The problem is not just the number of background stars, it is what those stars do to your detection algorithms. Modern survey telescopes produce images containing millions of sources per field, and sophisticated software pipelines are used to catalogue each source, measure its brightness and position, and classify it as a star, galaxy, or artifact. These pipelines work well in sparse fields where sources are well separated and each one can be cleanly measured. In crowded fields near the galactic plane, sources overlap, their light blends together, and the software struggles to disentangle individual objects. A faint Planet 9, already hovering at the edge of detectability, could easily be lost in the blended glow of 2 or 3 background stars that happen to sit near the same line of sight. Its feeble photons would be absorbed into the brighter combined signal of the stellar confusion, like a single drop of water falling into a river. There is a historical fact that illustrates this beautifully. When Clyde Tombaugh conducted his search for Pluto in the early 1930s, he deliberately focused on regions of the sky near the ecliptic but away from the densest parts of the Milky Way. He knew that searching through the galactic plane would be exponentially harder, and he structured his campaign to avoid the worst of the confusion. Pluto, as it happened, was located in a region of Gemini that was moderately crowded but not impossibly so. Tombaugh was strategic about where he pointed his telescope, and that strategy paid off. Planet 9 hunters face a less forgiving situation. The predicted orbit is so large and so uncertain that you cannot simply avoid the galactic plane. You have to search through it, because a substantial portion of the possible orbital positions lie within or near the worst confusion zones. Here's a quirky detail that adds another layer of frustration. The galactic plane is not just crowded with stars, it is also littered with interstellar dust, fine grains of carbon and silicate that absorb and scatter light, particularly at shorter wavelengths. This dust creates patches of extinction, regions where background objects appear dimmer and redder than they actually are. If Planet 9 is behind or near a patch of interstellar dust, its already feeble reflected light could be further dimmed and reddened, making it even harder to distinguish from the sea of faint red background stars that populate the galactic plane. The dust does not block infrared light as effectively, which is a point in favour of infrared searches. But as you learned earlier, infrared surveys have their own sensitivity limitations that have so far proven insufficient. Scholars still argue about how much of the galactic plane genuinely impedes the search, versus how much is simply an inconvenience that modern computational techniques can overcome. Some researchers have developed specialized algorithms designed to detect faint sources in crowded fields, using techniques borrowed from the search for exoplanet transits and gravitational microlensing events, both of which require finding subtle signals buried in noisy data. Others argue that no algorithm can fully compensate for the loss of sensitivity in the most confused regions, and that certain parts of the sky will remain effectively unsearchable until a telescope with significantly greater resolving power and sensitivity comes online. The debate is technical and ongoing, and it carries the quiet desperation of people who know that the answer to their question might be sitting right behind the galaxy's brightest curtain, visible in principle, but hidden in practice by the sheer exuberance of the Milky Way. You lie there and you think about that band of soft light you've seen on summer nights, and you realise it has been playing defence this whole time. The galaxy, your galaxy, the very structure you live inside, is actively interfering with the search for the solar system's most elusive resident. There is an irony in this that is almost too perfect to be accidental, as though the universe designed the problem not merely to be difficult, but to be specifically, personally, artistically difficult, each obstacle layered upon the last like blankets on a cold night. Now you are deep enough into this story to confront a possibility that has been lurking at edges, like a shadow you kept choosing not to look at directly. What if the evidence is wrong? What if the orbital clustering that launched this entire hunt is not a gravitational fingerprint at all, but an artifact of how and where we have looked? This is the observation bias argument, and it is one of the most contentious debates in modern planetary science. The kind of argument that splits conference rooms and fills email chains with the barely restrained fury of people who have spent years on opposite sides of a question that neither side can definitively resolve. The core of the argument is deceptively simple. The distant Kuiper Belt objects whose orbits appear to be clustered were not discovered by a single uniform survey covering the entire sky to a consistent depth. They were found by many different surveys, at many different times, using many different telescopes, each with its own patch of sky, its own sensitivity limits, and its own observing schedule. Some surveys covered the northern sky, but not the southern. Some were deep but narrow. Some were wide but shallow. The result is that our catalogue of extreme trans-Neptunian objects is not a random sample of what is out there. It is a biased sample, shaped by the particular directions astronomers happen to point their telescopes and the particular times they happen to observe. If you only look in certain parts of the sky, you will only find objects in those parts of the sky, and any apparent clustering in the orbits of those objects might simply reflect the clustering of your observations rather than any physical alignment. This argument was sharpened into a formal challenge in 2017 when researchers at the University of Michigan and elsewhere conducted careful analyses of the discovery circumstances of each known extreme trans-Neptunian object. They asked a pointed question. Given the sky coverage and sensitivity of the surveys that found these objects, would you expect to see an apparent clustering even if the true orbital distribution were random? The answer, according to their analysis, was uncomfortably close to yes. The selection effects introduced by the patchwork of surveys could, they argued, produce a false clustering signal that mimicked the appearance of gravitational shepherding. The implication was staggering. The entire case for Planet 9 might rest on a statistical illusion, a pattern conjured by the uneven way humans have sampled the outer solar system. Batagin and Brown pushed back. They argued that the selection bias analyses did not fully account for all the orbital parameters that showed clustering. It was not just the orientation of the orbits that was unusual, they said, but also the physical alignment of the orbital poles and the perihelion distances, multiple independent lines of clustering that would be extremely unlikely to arise from observational bias alone. They published updated analyses incorporating new discoveries and refined statistical methods, and their conclusion remained firm. The clustering was real, the probability of it being a coincidence remained extremely low, and a massive distant planet was still the best explanation. The academic back and forth that followed was meticulous and sometimes sharp, the kind of debate where footnotes become battlefields, and the precise definition of a statistical test becomes a hill worth dying on. Here is a historical fact that gives this debate a deeper resonance. The history of astronomy is littered with patterns that turned out to be artifacts. In the 19th century, the Italian astronomer Giovanni Schiaparelli reported seeing linear features on Mars that he called canali, meaning channels. Percival Lowell, whom you met earlier, interpreted these as artificial canals and built an entire theory of Martian civilization around them. The canals were ultimately revealed to be optical illusions, products of the humanized tendency to connect discontinuous features into straight lines when observing at the limits of resolution. The lesson is uncomfortable but important. The human desire to find order in noisy data is so powerful that it can create convincing patterns where none exist. Planet 9 skeptics invoke this lesson explicitly. The orbital clustering, they suggest, might be the canals of the 21st century, a pattern that feels compelling, but dissolves when you examine the data more carefully. Scholars still argue about the statistical robustness of the clustering, and the debate has evolved as new objects have been discovered. Each new extreme trans-Neptunian object that is found either strengthens or weakens the clustering signal, depending on its orbital properties and the circumstances of its discovery. Some recent additions to the catalogue have orbits consistent with the predicted alignment, which supporters cite as reinforcement. Others have orbits that do not fit the pattern neatly, which skeptics cite as evidence of dilution. The sample remains small, fewer than 24 objects with well-determined orbits in the relevant population, and small samples are notoriously susceptible to both real patterns and illusory ones. Increasing the sample size is critical, but doing so requires finding more distant objects, which brings you right back to all the observational challenges you've already encountered. The faintness, the slow motion, the vast sky, and the galactic confusion. There's a quirky philosophical dimension to this debate that does not get enough attention. The question of whether the clustering is real or illusory is not just a question about Planet 9. It is a question about how science handles evidence at the margins of detectability. How confident do you need to be before you declare a pattern genuine? How many alternative explanations do you need to rule out before you accept the most dramatic one? These are questions that haunt fields from particle physics to medicine, and the Planet 9 debate has become a case study in the challenge of drawing conclusions from sparse, biased, and uncertain data. You close your eyes a little more, and you feel the uncertainty settle around you like a second blanket, soft and not entirely unwelcome. Not everything needs to be resolved tonight. Some questions are better held gently than gripped tightly, and the question of whether Planet 9's evidence is real or illusory is one of those questions that improves with patience, and now the rivals arrive. Because in science, when a hypothesis sits on uncertain evidence, alternatives multiply like shadows at sunset, each one offering a different explanation for the same puzzling data, and each one quietly suggesting that maybe you do not need a planet at all. The orbital clustering of distant Kuiper Belt objects might be the signature of something far stranger than a hidden world, or it might be the signature of nothing at all, and the parade of alternative theories is as creative as it is humbling. The simplest alternative is the one you've already encountered: pure statistical coincidence amplified by observation bias. No planet, no exotic physics, just the inevitable result of looking at a small sample through an uneven observational window. This is the null hypothesis, the boring explanation, and in science the boring explanation always gets to go first because it demands the least new physics. If the clustering dissolves as more objects are discovered, this explanation wins by default, and Planet 9 joins Lowell's Martian canals in the gallery of compelling patterns that turned out to be noise. It is not a glamorous ending, but science has never promised glamour, only accuracy, and sometimes accuracy is a cold cup of water when you are hoping for champagne. But the alternatives get considerably more exotic from here. One of the most intriguing was proposed in 2019 by physicists Jakob Schultz and James Unruh. who suggested that the gravitational effect attributed to Planet 9 might be caused not by a planet, but by a primordial black hole. You will explore this idea in more depth later, but the headline version is this. A black hole with a mass of 5 to 10 Earths would be roughly the size of a grapefruit. It would exert the exact same gravitational influence as a planet of the same mass, and it would be essentially invisible to every detection method currently employed. No reflected sunlight because it has no surface, no thermal radiation because its Hawking temperature is negligibly above absolute zero. Just gravity, silent and dark, sculpting distant orbits from the void. The idea sounds like science fiction, but primordial black holes are a legitimate theoretical prediction, objects that might have formed in the extreme density fluctuations of the very early universe, and their existence has never been ruled out in the relevant mass range. If the clustering is real and its cause is a primordial black hole rather than a planet, the search as currently conceived is not just difficult, it is fundamentally misdirected. Another alternative dispenses with a single massive object entirely and replaces it with a collective effect. Some researchers have proposed that the gravitational influence attributed to Planet 9 could be produced by a disk or ring of small icy bodies in the outer solar system, none individually massive but collectively exerting enough gravitational pull to shepherd the observed orbits. This idea has a certain democratic appeal, replacing one king with a parliament of pebbles, but it faces significant challenges. Simulations suggest that a self-gravitating disk of small bodies would need to have a total mass comparable to several Earths to reproduce the observed clustering, and such a disk would itself be difficult to explain dynamically. Where did all that mass come from? Why has it not been detected by existing surveys? The disk hypothesis trades one invisible object for billions of invisible objects, which is arguably not an improvement. Then there are the modified gravity proposals, which take a completely different approach. Instead of adding unseen mass to the solar system, these theories suggest that the laws of gravity themselves might behave differently at extreme distances. Modified Newtonian dynamics, or MOND, originally proposed by physicist Mordechai Milgram in the 1980s to explain galaxy rotation curves without dark matter, has been invoked by some researchers as a possible framework for understanding the outer solar system's anomalies. In this view, the clustering of distant orbits is not caused by a hidden mass, but by a subtle deviation from Newtonian gravity that only manifests at very low accelerations, the kind of accelerations experienced by objects hundreds of astronomical units from the Sun. This is a minority position, and a controversial one, because MOND has its own substantial problems as a theory, but it represents the kind of radical rethinking that emerges when conventional explanations remain unconfirmed for long enough. And there is a historical fact that lends this proliferation of alternatives a certain poetic symmetry. Before Neptune was discovered, astronomers debated whether the anomalies in Uranus's orbit should be attributed to an unseen planet or to a modification of Newton's gravitational law. The planet explanation won spectacularly when Gall found Neptune exactly where Leverrier predicted it. But the debate itself was genuine and scientifically productive, forcing researchers to sharpen their predictions and their methods. The Planet 9 debate is following the same arc, with the same tension between the conservative option of adjusting the mass inventory and the radical option of adjusting the physics. Scholars still argue about which alternative, if any, should be taken most seriously. The primordial black hole hypothesis has attracted significant theoretical interest, but is almost impossible to test with current technology. The small body disk hypothesis is dynamically plausible, but lacks observational support. The modified gravity proposals are intriguing but remain outside the mainstream, and hovering above all of them is the original Planet 9 hypothesis, still the most parsimonious explanation for the full set of observed anomalies, but still lacking the one thing that would silence every rival, a direct detection. You drift a little deeper into your pillow and you realise that the outer solar system is not just dark. It is contested, a battlefield of ideas where the evidence is thin enough that multiple incompatible theories can coexist, each one casting the others in shadow, each one waiting for a single observation to crown it or bury it. Behind every prediction about Planet 9, behind every estimated orbit and every brightness calculation, there is a computer working furiously, running simulations that attempt to model the behaviour of the outer solar system over billions of years, and this is where you encounter yet another layer of difficulty, one that lives not in the telescope or the sky, but in the mathematics itself. Simulating the outer solar system is extraordinarily hard, and the uncertainty in those simulations feeds directly into the uncertainty of the search. The fundamental problem is called the n-body problem, and it has been tormenting physicists since Newton first laid down the laws of gravitation. If you have two objects interacting gravitationally, you can solve their motion exactly. The math is clean, the orbits are elegant ellipses, and everything is predictable for all eternity. Add a third body, and the situation becomes dramatically more complicated. The three-body problem, in the general case, has no closed-form solution. The motions become chaotic, meaning that tiny differences in initial conditions can lead to wildly different outcomes over time. Now add the Sun, 8 known planets, thousands of Kuiper Belt objects, the gravitational influence of passing stars over billions of years, and the hypothetical Planet 9 itself, and you have a computational nightmare of the first order. The n-body problem at this scale does not have an analytical solution. It can only be solved numerically by breaking time into tiny steps and computing the gravitational forces at each step, accumulating the answer through brute repetition. Modern n-body simulations are sophisticated and powerful. Researchers use specialized algorithms that efficiently compute gravitational interactions, adaptive time-stepping methods that concentrate computational effort where it is most needed, and parallelize codes that distribute the work across hundreds or thousands of processor cores. But even with all of this, the chaotic nature of the outer solar system imposes fundamental limits on what you can know. In a chaotic system, errors accumulate exponentially over time. A tiny uncertainty in the initial position of a single Kuiper Belt object, an uncertainty that might be smaller than the width of an atom, can grow over billions of years into an uncertainty that spans the entire solar system. This means that when you run a simulation of the outer solar system forward or backward in time over the age of the solar system, the specific details of the final state are exquisitely sensitive to the input parameters. For the Planet 9 search, this chaos creates a maddening problem. The simulations that Batagin and Brown used to predict the planet's existence tell you that a massive perturber on a distant orbit can produce orbital clustering. They can tell you the approximate mass, distance and inclination of the perturber, but they cannot tell you precisely where on its orbit the planet is right now, because that answer depends on the exact initial conditions of the solar system 4.5 billion years ago, conditions that are known only approximately. The simulations produce probability distributions, regions of the sky where the planet is more or less likely to be, but those distributions span hundreds of square degrees. It is like knowing that someone is in New York City but not knowing whether they are in Manhattan or Staten Island. The information narrows the search but does not resolve it. There is a mainstream historical fact that puts this computational challenge in perspective. When Leverrier predicted Neptune's position in 1846, his calculation was essentially a two-body perturbation problem. He needed to account for the gravitational influence of one unknown planet on one known planet, Uranus, and the mathematics, while laborious was tractable with pen and paper. The entire computation took months of manual arithmetic, but produced a prediction accurate to within 1 degree. Planet 9's prediction involves dozens of interacting bodies, billions of years of dynamical evolution, and a chaotic system where small errors compound relentlessly. Leverrier had the mathematical equivalent of a pocket calculator. Planet 9 hunters need the equivalent of a supercomputer, and even the supercomputer shrugs and offers probabilities rather than certainties. Here is a quirky detail that illustrates the computational scale involved. A single high-resolution N-body simulation of the outer solar system, tracking the evolution of thousands of test particles under the influence of the giant planets and a hypothetical Planet 9 over 4 billion years, can take days to weeks of continuous computing time on modern hardware. And to explore the full range of possible Planet 9 parameters — mass, semi-major axis, eccentricity, inclination, argument of perihelion — you need to run not one simulation but thousands, each with slightly different initial conditions. Researchers have estimated that a comprehensive parameter survey requires millions of CPU hours, the kind of computational budget that demands time on national supercomputing facilities and the patience of a monk. Scholars still argue about how to best use this computational power. Some researchers favour running fewer, higher-resolution simulations that capture the fine details of individual orbital interactions. Others prefer running vast ensembles of lower-resolution simulations that sample the parameter space more broadly, sacrificing precision for coverage. Machine learning techniques have been proposed as a way to shortcut the process, training neural networks on simulation outputs to interpolate the results without running every combination explicitly. These approaches are promising but introduce their own uncertainties, because a neural network is only as good as the training data it learns from. And if the training data misses a critical region of parameter space, the network will confidently produce wrong answers, which is arguably worse than producing no answer at all. The computational obstacle is invisible to most people outside the field. It does not make for dramatic headlines or compelling telescope photographs, but it is one of the deepest reasons why Planet 9 remains unfound. The universe is not only hiding the planet behind distance and darkness and confusion, it is hiding the planet behind chaos itself, behind the mathematical reality that even a perfect simulation cannot tell you exactly where to look. You breathe slowly and you feel the weight of that complexity settling into the quiet spaces of the room, not as anxiety but as a kind of awe. The solar system is a 4.5 billion-year-old puzzle, and the pieces are still moving. But there is a reason astronomers have not surrendered. A reason the search continues despite every obstacle you have drifted through tonight. That reason has a name, and it is sitting on a mountaintop in Chile, still under construction, and it represents the single greatest hope for finding Planet 9 within the next decade. It is called the Vera C. Rubin Observatory, and it is about to change the way humanity sees the sky. Named after the American astronomer Vera Rubin, whose pioneering observations of galaxy rotation curves provided some of the strongest evidence for dark matter, the observatory is perched on Cerro Pachon in the Chilean Andes at an elevation of about 2,500 meters, where the air is thin and dry and the seeing conditions are among the best on the planet. The telescope itself, formerly called the Simony Survey Telescope, has an 8.4 meter primary mirror, which places it among the largest optical telescopes in the world. But what makes it extraordinary is not just its size. It is the camera mounted at its focus, the largest digital camera ever built for astronomy, a 3 billion pixel monster that can photograph a patch of sky roughly 40 times the area of the full moon in a single exposure. This combination of aperture and field of view is unprecedented. The Rubin Observatory was designed from the ground up to do one thing supremely well: survey the entire visible southern sky repeatedly, deeply, and quickly. The observatory's primary mission is called the Legacy Survey of Space and Time, or LSST, and the plan is breathtakingly ambitious. Over 10 years, the telescope will photograph the entire accessible sky, approximately 800 times, building up an extraordinarily deep multi-epoch map of everything that shines, moves, flickers, or explodes. Each patch of sky will be revisited every few nights, and the accumulated data will reach objects as faint as magnitude 27, which is deep enough to detect Planet 9 at most of its predicted distances, assuming its brightness falls within the range of current estimates. The survey will generate roughly 20 terabytes of raw data every single night, an avalanche of information that will be processed by automated pipelines designed to detect transient events, moving objects, and anything that changes over time. For the Planet 9 search, the LSST offers something that no previous survey has provided: the combination of depth, sky coverage, and cadence needed to systematically sweep the search space. Remember those frustrating gaps between existing surveys, the patches of sky not covered deeply enough, the regions where cadence was too sparse to catch a slow-moving object? The LSST is designed to fill those gaps. Its repeated observations will enable shift and stack techniques on an unprecedented scale, combining hundreds of exposures of the same field to push below the single exposure detection limit and potentially catch objects that are individually too faint to appear in any one image. If Planet 9 is out there and it is brighter than roughly magnitude 26 or 27, the LSST should, in principle, be able to find it within its 10-year survey. There is a historical fact embedded in this optimism that is worth noting. Vera Rubin herself spent much of her career battling skepticism. Her early work on galaxy rotation was dismissed by many in the male-dominated astronomical establishment, and her evidence for dark matter was initially met with resistance. She persisted, and her observations eventually helped reshape our understanding of the universe. Naming the observatory after her was a deliberate tribute, and there is a satisfying poetry in the possibility that a telescope bearing her name might discover a planet whose existence is inferred from gravitational evidence, just as dark matter's existence was inferred from the gravitational evidence she championed. But even the Rubin Observatory comes with caveats, and you should hear them, because they temper the hope with the kind of practical reality that the outer solar system specializes in delivering. The first caveat is sky coverage. The observatory is located in the southern hemisphere, which means it can only observe the southern sky and a portion of the sky near the celestial equator. A significant fraction of the northern sky is permanently inaccessible. If Planet 9 happens to be in the northern celestial hemisphere, the LSST will not see it, and the search in that region will depend on northern hemisphere telescopes, with less favourable combinations of depth and field of view. The second caveat is cadence. While the LSST will revisit each field frequently, the specific cadence is optimised for the survey's many competing science goals, including supernova detection, asteroid tracking, and cosmological measurements. The cadence that is optimal for finding distant slow-moving objects is not necessarily the same cadence that is optimal for catching supernova, and the final observing strategy involves compromises that may leave the Planet 9 search slightly less efficient than a dedicated campaign would be. Here is a quirky detail that captures the tension. The LSST science community spent years debating the optimal cadence through a process that involved hundreds of white papers, simulations, and committee meetings. The Planet 9 search was one of many science cases competing for cadence optimization, and while it received serious attention, it did not dominate the final strategy. The observatory is a shared resource, and Planet 9, however dramatic its discovery would be, is one question among thousands that the LSST is designed to address. Scholars still argue about whether the LSST will definitively resolve the Planet 9 question. Optimists point to its extraordinary depth and coverage, and argue that if the planet exists within the predicted parameter space, the LSST will find it or severely constrain its properties. Pessimists note that if Planet 9 is near aphelion, at perhaps 800 or 1,000 astronomical units, it could be fainter than magnitude 27 and beyond even the LSST's reach. The observatory is the best tool humanity has ever built for this search, but the universe is under no obligation to place the answer within reach of even the best tool. You settle a little deeper and you hold that tension, the hope and the caveat, balanced together like two weights on a scale that refuses to tip. While the professionals build their billion-dollar observatories and run their supercomputer simulations, there is another branch of the search happening in living rooms and home offices around the world, and it carries a charm that no institutional telescope can replicate. Citizen science, the practice of enlisting the public to help with scientific research, has a surprisingly long and noble history in astronomy, and the hunt for Planet 9 has embraced it with open arms and cautious expectations. The flagship project is called Backyard Worlds, Planet 9, launched in 2017 by a team led by astrophysicist Mark Kushner at NASA's Goddard Space Flight Center. The concept is elegantly simple. The WISE and near-WISE infrared surveys generated an enormous volume of data, far more than any small team of professional astronomers could visually inspect. Automated algorithms have been run on the data, of course, but algorithms have blind spots. They struggle with artifacts, image edges, diffraction spikes from bright stars, and the kinds of subtle anomalies that a trained human eye can catch almost instinctively. So the Backyard Worlds team uploaded the WISE data to a web platform and invited anyone with an internet connection to flip through the images, looking for faint objects that moved between epochs. Thousands of volunteers signed up. Some were amateur astronomers with backyard telescopes. Some were retired teachers. Some were teenagers who stumbled onto the project through social media. And together, collectively, they began sifting through the cosmic haystack with a thoroughness that no algorithm could match on its own. The results have been genuinely remarkable, though not in the way the project's name might suggest. Backyard Worlds volunteers have not found Planet 9, but they have discovered hundreds of previously unknown brown dwarfs, objects that sit on the boundary between the largest planets and the smallest stars, too massive to be planets, but too cool to sustain hydrogen fusion. Some of these brown dwarfs are among the coldest ever identified, with temperatures barely above room temperature in the astronomical terms, and their discovery has advanced our understanding of the low-mass end of stellar and substellar populations. The volunteers have also flagged numerous interesting moving objects in the outer solar system, and identified co-moving star systems that professionals had missed. The scientific output of the project, measured in peer-reviewed papers and new catalogue entries, has been substantial and is a testament to the power of distributed human attention. There is a mainstream historical precedent for this kind of discovery that is worth savouring. In 1781, when William Herschel discovered Uranus, he was essentially a citizen scientist, a self-taught astronomer with a homemade telescope who happened to be more meticulous than most professionals. The tradition of amateur contributions to astronomy runs deep, from comet discoveries by dedicated backyard observers to the identification of unusual variable stars by volunteers in the American Association of Variable Star Observers. The night sky has always been a democratic frontier, and the idea that Planet 9 might be found not by a world-class observatory, but by someone sitting at a kitchen table scrolling through infrared images carries a romantic appeal that the scientific community quietly enjoys even as it manages expectations. But romantic appeal should not be confused with probability. The chances of a citizen scientist finding Planet 9 through the Backyard Worlds platform are, honestly, very small. The WISE data has sensitivity limits that you already know about, and Planet 9 is likely below those limits at most of its predicted positions. What citizen science does offer is a complementary search channel, a way to catch objects that automated pipelines might have missed due to artifacts or edge effects, and a way to engage the public in a genuine scientific endeavour rather than a passive spectacle. There is real scientific value in having hundreds of thousands of human eyes scanning data, even if the specific quarry remains elusive, because those eyes find things that nobody was specifically looking for, and surprise discoveries are the lifeblood of astronomy. Here is a quirky detail that captures the serendipitous magic of citizen science. In 2018, a Backyard Worlds volunteer in Tasmania identified a peculiar object that turned out to be one of the oldest and coldest white dwarfs ever discovered, surrounded by rings of dusty debris. The volunteer was not looking for white dwarfs. Nobody had asked him to find one. He simply noticed something odd in the images, flagged it, and professional follow-up confirmed it as a scientifically significant discovery. This is how citizen science works at its best, not as a targeted search, but as a wide net cast by curious minds, catching whatever the universe decides to throw into it. Scholars still argue about the optimal balance between automated algorithms and human visual inspection in large survey datasets. Machine learning has made enormous strides in recent years, and modern neural networks can classify astronomical sources with accuracy that rivals or exceeds human performance in many tasks. But the edge cases, the weird objects, the things that do not fit neatly into any category, are often where the most interesting discoveries hide, and human intuition still has an advantage in recognizing things that look simply wrong in ways that a training dataset never anticipated. The Planet 9 search benefits from both approaches, the tireless precision of algorithms and the flexible curiosity of human volunteers, and if the planet is ever found, the discovery might well depend on a partnership between the two. You think about all those people in their homes scattered across time zones, clicking through images of the infrared sky in the hope of spotting a faint moving dot that could rewrite the textbooks. There is something deeply comforting about that image, all those quiet acts of curiosity happening simultaneously around the world, each one a small rebellion against the vastness and indifference of the universe. The search for Planet 9 is not just a scientific problem, it is a communal project, a shared act of looking, and even if the planet is never found, the looking itself has value. You close your eyes a little more and let that thought settle, warm and unhurried, like a candle flame reflected in a dark window. Now you need to go back to that grapefruit. Remember the primordial black hole idea that surfaced briefly during the parade of alternative theories? You let it pass by without much scrutiny at the time, but it deserves a longer look because it is one of the most fascinating and unsettling possibilities in the entire Planet 9 saga, and it illuminates just how strange the universe is willing to be when you're not paying attention. The hypothesis was formally proposed in 2019 by Jakub Scholz of Durham University and James Unruh of the University of Illinois at Chicago. Their argument began with a deceptively simple observation. Everything we know about Planet 9 comes from its gravitational influence on distant Kuiper Belt objects. We have never seen it. We have never detected its light, reflected or thermal. All we have is gravity, and gravity does not care what shape its source takes. A 5 Earth mass planet and a 5 Earth mass black hole would pull on surrounding objects in exactly the same way. From a gravitational perspective, They're identical. The orbits of the distant Kuiper Belt objects would cluster the same way, the dynamical arguments would hold the same way, and every simulation Batagin and Brown ever ran would produce the same results. The only difference is what you see when you point a telescope at the source, and in the case of a primordial black hole, the answer is nothing. Absolutely, profoundly, maddeningly nothing. A primordial black hole with 5 Earth masses would have a Schwarzschild radius of roughly 9 centimeters. That is the size of a tennis ball, or a large grapefruit, depending on which fruit you find more evocative in a conversation about collapsed space-time. This object would not emit visible light, because it has no surface to reflect sunlight. It would not emit meaningful thermal radiation, because the Hawking radiation from a black hole of this mass has a temperature so close to absolute zero that it is billions of times colder than the cosmic microwave background. It would not show up in infrared surveys, radio surveys, or any electromagnetic survey of any kind. It would be, for all practical purposes, invisible. The only way it interacts with the universe is through gravity, and gravity is exactly what led us to suspect its existence in the first place. The logic is circular in the most frustrating possible way. You infer its presence from gravity. You try to confirm its presence with light. Light finds nothing. Gravity shrugs. There is a mainstream scientific context that makes this hypothesis more than just a clever thought experiment. Primordial black holes are a legitimate prediction of certain models of the very early universe. In the first fraction of a second after the Big Bang, density fluctuations in the expanding cosmos could have caused some regions to collapse directly into black holes without ever forming stars. These primordial black holes could span a wide range of masses, from microscopic to many times the mass of the Sun, and unlike black holes formed from dying stars, they would not be accompanied by the usual astrophysical signatures like accretion disks or X-ray emission. They would simply be floating through space, invisible, interacting with nothing except through gravity. Decades of the research have constrained the possible abundance of primordial black holes at various mass scales, but the range around 5 to 15 Earth masses remains relatively unconstrained. There is, as of right now, no observational evidence that definitively rules out a primordial black hole of this mass lurking in the outer solar system. Schultz and Unruh went a step further. They noted that if the object were a primordial black hole, it might occasionally interact with small bodies in the outer solar system, drawing in comets or Kuiper Belt fragments that would produce brief flares of radiation as the material was heated during infall. These flares would be faint and transient, but they might be detectable by a sufficiently sensitive survey if you knew where to look and when to look. The proposed method of detection is almost whimsically indirect. Instead of searching for the black hole itself, you search for the tiny flashes of light produced when it eats something. It is like trying to find an invisible cat by scattering treats around the room and watching for the treats that disappear. Here is a quirky detail that adds a layer of delightful absurdity. If the object is a primordial black hole, then the Planet 9 search as currently designed is not just failing because the target is faint. It is failing because the target fundamentally cannot produce the signal that telescopes are looking for. Every optical and infrared survey that has come up empty would have come up empty even with perfect sensitivity and perfect sky coverage because there is no light to detect. The search strategy itself is built on the assumption that the gravitational source is a planet, and if that assumption is wrong, then years of observations have been perfectly executed searches for something that was never there. It is not that the haystack is too large or the needle too small, it is that the needle is made of something a magnet cannot attract. Scholars still argue about how seriously to take the primordial black hole hypothesis. Some regard it as a creative but speculative alternative that should be kept in mind but not prioritized over the planetary explanation. Others argue that the inability to detect Planet 9 after years of searching is itself indirect evidence that the source might not be a conventional planet, and that unconventional detection strategies should receive more attention and funding. The debate touches on deep questions about how science allocates resources between mainstream hypotheses and exotic alternatives, and there is no easy answer. You lie there in the dark and you think about a grapefruit-sized object with a mass of 5 Earths drifting silently through the outer solar system, bending space around it, swallowing any photon that wanders too close, and answering every question with silence. It is either the most terrifying or the most peaceful image you have encountered tonight, and you're too comfortable to decide which. There's a dimension to this entire story that has nothing to do with telescopes or simulations or orbital mechanics, and it has been humming quietly beneath every section you have drifted through tonight. It is the psychological dimension, the deeply human part. The reason this search captivates people who will never look through a telescope and could not name a single Kuiper Belt object if their lives depended on it. Planet 9 is burrowed into the collective imagination not because of what it is, but because of what it represents. The unfinished map, the blank space at the edge of knowledge, the possibility that something enormous is hiding in your own backyard and you simply have not turned around to see it yet. Humans have always been uncomfortable with incomplete maps. There is a neurological basis for this. Your brain is a prediction engine, constantly building models of the world and filling in gaps with expectations and assumptions. When a gap resists being filled, when a question lingers unanswered, the brain generates a low-level discomfort that psychologists call the need for cognitive closure. This is the same itch that makes you want to finish a half-read book, solve an abandoned crossword, or look up the answer to a trivia question at 3 a.m, even though you have work tomorrow. Planet 9 activates this itch on a cosmic scale. We have mapped the solar system with extraordinary precision. We have sent spacecraft to every known planet. We have catalogued hundreds of thousands of asteroids and comets. And yet there might be an entire world out there that we have not found. That gap in the map is intolerable to the pattern-completing machinery of the human mind, and it explains why the Planet 9 hypothesis generates so much public fascination relative to its current evidential status. There is a mainstream historical echo here that runs remarkably deep. The obsession with undiscovered planets is not a modern phenomenon. In the 19th century, astronomers searched for Vulcan, a hypothetical planet orbiting closer to the Sun than Mercury, proposed to explain anomalies in Mercury's orbit. Vulcan was never found because it does not exist. The anomalies were eventually explained by Einstein's general theory of relativity, which showed that Newton's gravity was slightly wrong in the strong gravitational field near the Sun. But for decades, serious astronomers dedicated serious telescope time to searching for Vulcan, and some even claim to have observed it during solar eclipses, seeing what they wanted to see in the blinding glare of the Sun's corona. The parallel to Planet 9 is uncomfortable but instructive. The gravitational anomaly was real, the interpretation was wrong, and the human desire to fill the gap with a planet was so strong that it produced false sightings and sustained a search long after the evidence had grown thin. Percival Lowell's Planet X quest carries the same psychological signature. Lowell was not a careless scientist. He was brilliant, meticulous, and utterly convinced that the patterns he saw in the data demanded a planetary explanation. His conviction drove him to build an observatory, fund decades of observations, and dedicate the last years of his life to a search that was, in hindsight, based on flawed data. The gravitational residuals he was chasing were mostly measurement errors, and the planet Tombaugh eventually found had nothing to do with Lowell's predictions. Yet Lowell's story is not a cautionary tale about stupidity. It is a cautionary tale about the seductive power of an incomplete map. When the brain sees a gap, it fills it with whatever is most intellectually satisfying, and a hidden planet is almost always more satisfying than a measurement error. Here is a quirky detail that connects this psychology to the modern era. When Batagin and Brown published their 2016 paper, internet searches for Planet 9 spiked to levels that dwarfed searches for many confirmed astronomical discoveries. The public was more excited about a planet that might exist than about planets that definitely do. This tells you something important about human cognition. Certainty is reassuring but dull. Uncertainty is uncomfortable but thrilling. The possibility of Planet 9 occupies a sweet spot in the landscape of human curiosity, definite enough to feel real, but unresolved enough to feel urgent, and that sweet spot is precisely where obsession lives. Scholars still argue about whether this psychological pull introduces bias into the scientific process itself. Some philosophers of science have suggested that the Planet 9 hypothesis benefits from a kind of confirmation bias, where researchers unconsciously weight evidence that supports the planet's existence more heavily than evidence that undermines it. Others counter that the scientific method, with its peer review and replication requirements, is specifically designed to counteract such biases, and that the ongoing debate between Planet 9 supporters and skeptics is evidence that the system is working as intended. The truth, as usual, probably lies somewhere in the uncomfortable middle. Scientists are human. Humans want to find things. And a planet at the edge of the solar system is a find so monumental that the desire to discover it could subtly shape how ambiguous evidence is interpreted, even among the most rigorous researchers. You lie in the dark and you think about maps. You think about the blank spaces at the edges of old nautical charts, where cartographers used to write, "Here be dragons," or sketch sea monsters coiling through imagined waves. Those blank spaces were not evidence of dragons, they were evidence of ignorance, and the monsters were the mind's way of making the ignorance feel populated, less empty, less threatening. Planet 9 might be the dragon on the modern map of the solar system, a compelling creature drawn into the blank space beyond Neptune because the alternative, a blank space with nothing in it, is somehow harder to accept. Or it might be real. It might be out there right now, a cold, dark world with the mass of several Earths, orbiting in silence, utterly indifferent to the psychological needs of the species trying to find it. You breathe in, you breathe out, and you let both possibilities coexist because tonight is not a night for resolving things. It is a night for holding them gently. And so you arrive at the end, or at least at the edge of what can be said tonight about the search for Planet 9. You have travelled an extraordinary distance, not just in astronomical units, but in ideas, from the accidental discovery of Uranus in a musician's backyard to the computational chaos of billion-year simulations. From the faint infrared whispers of WISE to the romantic possibility of a citizen scientist in Tasmania, spotting something that every professional observatory missed. You've met the gravitational breadcrumbs and the orbital clustering, the inverse square law and the galactic confusion, the blink comparator and the 3 billion pixel camera. You have considered the possibility that the thing you're searching for is not a planet at all, but a grapefruit-sized hole in space-time, drifting silently through the outer dark, answering every question with gravity and nothing else. And through all of it, the central truth has remained unchanged. Despite every indirect clue, despite every compelling simulation, despite the focused efforts of some of the most talented astronomers in the world, Planet 9 has not been found. It might not be found for decades. It might not exist at all. That last possibility deserves to sit with you for a moment, because it is the one that most discussions of Planet 9 try to avoid. The hypothesis is elegant, The math is persuasive and the gravitational evidence is tantalizing. But elegance is not proof. Persuasion is not detection. And the history of astronomy, as you've seen tonight, is littered with elegant hypotheses that turned out to be wrong. Vulcan was elegant. Lowell's Planet X was elegant. The Martian canals were elegant. Each one was supported by real observational anomalies, championed by serious scientists, and ultimately demolished by better data or better theories. Planet 9 could follow the same path. The orbital clustering could dissolve as more trans-Neptunian objects are discovered, and the statistical picture sharpens. The alternative explanations, the self-gravitating disk, the modified gravity, the observation bias, could prove more robust than the planetary hypothesis. Science is not a story with a guaranteed climax. Sometimes the mystery simply remains a mystery, and the blank space on the map stays blank. But here is the thing that makes the search worth celebrating regardless of the outcome. Every telescope hour spent hunting for Planet 9 has produced valuable science. The surveys have discovered hundreds of new Kuiper Belt objects, refined our understanding of the outer solar system's structure, and pushed the boundaries of observational technology. The simulations have deepened our knowledge of orbital dynamics and chaos. The citizen science projects have engaged millions of people in the process of discovery and found brown dwarfs and white dwarfs that nobody was looking for. The debate between Planet 9 supporters and skeptics has sharpened the statistical tools used across all of observational astronomy. Even if Planet 9 is never found, the search will not have been wasted. It will have been one of the most productive wild goose chases in the history of science, and that is not a bad legacy for a planet that might not exist. There is a historical fact that closes this loop with a certain grace. When Clyde Tombaugh searched for Planet X in the 1930s, he did not find the massive planet Lowell had predicted. He found Pluto, a tiny icy world that answered a different question than the one he was asking. The search produced something unexpected, something beautiful, something that reshaped our understanding of the solar system, even though it was not the thing anyone was looking for. The Vera Rubin Observatory, when it begins its survey, may do the same. It may not find Planet 9, but it will almost certainly find things that nobody has imagined yet. Objects and phenomena lurking in the data like gifts hidden in a dark room, waiting to be stumbled upon by someone patient enough to keep looking. Scholars still argue about whether the search for Planet 9 will be resolved within the next decade, or whether it will stretch on for generations, becoming one of those slow-burning scientific questions that each era revisits with slightly better tools and slightly refined expectations. There is no consensus, and that is fine. Some questions are too large and too deep to be answered on a schedule, and now the room around you softens. The story has carried you far enough, and the darkness outside your window is no longer the cold darkness of the outer solar system. It is the warm darkness of a night that is simply doing what nights do, wrapping itself around you, slowing your thoughts, letting the sharp edges of facts and figures blur into something gentler. The distant Kuiper Belt objects are still out there, tracing their long, slow ellipses through the void. The telescopes are still scanning, their detectors patiently counting photons one by one. Somewhere, a citizen scientist is clicking through infrared images before bed, and somewhere, a graduate student is watching a simulation run on a screen that glows faintly in a dark office. The search continues. It does not need you to stay awake for it. Let your breathing slow, let the numbers dissolve, let the orbits and the estimates and the debates settle like snow on a quiet field, covering everything in a soft white silence that asks nothing of you. The solar system is vast and patient, and whatever is hiding in its outermost reaches will still be there tomorrow, and the day after, and the century after that. You do not need to find it tonight. You do not need to find anything tonight. You only need to let go gently, the way a leaf lets go of a branch in autumn, not because it is forced, but because the time has come and the wind is kind. The darkness is not empty. It is full of questions, and questions are just the universe's way of keeping you company while you sleep, so close your eyes. Let the last image be something simple, a single point of light at the edge of an enormous orbit, moving so slowly it might as well be still, glowing so faintly it might as well be a dream. It is out there, or it is not. Either way, the sky is beautiful and you are warm and the night is yours.